Hello, and we're back to part 3, lesson 3.1. The reason we're doing this in small sections is so that you can stop the video and it doesn't interfere. Smaller sections are easier for me to handle as well, too. So hang in there. So you guys, we were looking at these two functions. 1 plus 1 over x to the x is approaching, the function is approaching the value e, 2.718, etc. And if you watch the YouTube video of the guy explaining the natural base e, then that should make sense to you. Our culture, mathematically, we seem to bow down to the number 10. Everything's base 10. But e is a number that explains things that rapidly increase and decrease. I wanted you to look at these two functions. We replaced in the approximation of e 1 over x with two values 3 and 4. And what I wanted you to see in the case of the first one, e to the third power, sorry I didn't get that calculated, e to the third power is 20.1. 20.1. E to the fourth power, 54.6. 54.6. What I wanted you to see with these two functions, f of x, if we graph that in the coordinate plane, the value y equals 20.1, a horizontal line, is being approached by the function 1 plus 3 over x to the x. When x is 0, the function's undefined, and we see the function coming up slowly and approaching that horizontal line as an asymptote, 20.1. In, not contrast, in relation to that, h of x, the value e to the fourth, 54.6, the function 1 plus 4 over x to the x is approaching that line. I just thought this was fascinating, interesting. Talked to a couple of our math teachers and haven't really come up with a good explanation yet. But it's up for discussion. We should talk about it in class. Right now, what I'd like you to do, reading example 6 on page 185, we can see that they are simply taking the function f of x equaling e to the x and substituting different values for that exponent, that exponential function e to the x, and calculating those values. Example 7, graphing natural exponential functions. What they've done in example 7, two of them, part A, f of x is 2 times e to the power 0.24x, and then they want to compare and contrast that to the function g of x, which is 1/2 e to the negative 0.58x. There should be two things that you would want to compare and contrast with this, one being the coefficient to e, or the value being multiplied by e. In part A, 2, let's look at that graph. When we have 2e and x is 0, e to the 0 is just 1. When x is 0, e to the 0 is 1, and our y-intercept is 2. The other one, g of x, in contrast, when x is 0, our entire exponent is 0, e to the 0 is 1 again, and our y-intercept is 1/2. So there's two comparisons that we can make. Now in f of x, we have a positive exponent, and so we should see a function increasing, we should see our function increasing or growing from left to right, or negative infinity to positive infinity. And then when we look at our negative exponent, the things or conclusions you guys should be making is we have that different y-intercept and we have a decay. I'd like you to try exercise 47 and then come back and we'll talk about that. Please pause and work on problem 47 in your problem set. So in looking at problem 47, the directions ask us to use a graphing utility to construct a table of values for the function and then sketch the graph of the function, identify any asymptotes of the graph. Our function s of t equaling 2 times natural base e to the point 1, 2, t. We're going to look at that more closely here in the next section. I've just put some values up there, but what I want you to see, that coefficient to that exponent, we have a very, very small value. And if we look at this graph, I'm going to graph the easiest point here first. When t is 0, s is 2, and we have a positive coefficient. We know this is a growth function, but we can see it laying out with much more gradually than some of the other functions that we've dealt with, where that coefficient to the exponent is a much larger value. Okay, so using graphing utility, coming up with some values and graphing these natural log e, natural base exponential functions. What I'd like you to do right now is turn to sorry. Let's go ahead and turn to page 186. We're going to look at applications of graphing exponential functions, and in the next lesson, log functions. So at the top of 186, we're talking about money, the growth of money, which should be a fascinating thing to most teenagers, especially those with dreams of going into college. It takes lots of money to go to college these days. So we want to be smart with our money and understand it. At the top of 186, it says one of the most familiar examples of exponential growth is an investment earning continuously compounded interest. Well, I'd like to say that this is fiction. In mathematics, it's theory. You won't find a bank that compounds your interest continuously, but it is a discussion we can have. So suppose we have a principal value invested in an annual interest rate. So P, capital P, will be our principal. In our formula, rate, R, the reason I said oops is I thought PAL stood for Principal Waslowski, and the principle of money was PLE. But we'll just keep moving on. The book has PAL. Now the interest rate are compounded once a year. If the interest is added to the principal at the end of the year, you see the table that they've come up with. The principal at the end of 0 years is all you have. At the end of 1 year, you have principal and 1 plus the interest rate. Why 1 plus? You have 100%. Let's say we had 2.5% interest. We have 1.025 times our principal. So the 1 represents 100% of our investment plus the rate. Well, if you look at that table, you can see how the formula starts to emerge. The formula for compound interest, the principal, at the end of a certain amount of time, is going to equal principal times 1 plus the rate, as we just saw, 1 plus the rate for t years. To accommodate more frequent, so this, when we see it this way, this is for compounded annually. Does everybody know what that means? Compounded annually. Well, annually means once a year. 1 per year. So we know if we're compounding annually that we can use this formula. It says to accommodate more frequent compoundings, quarterly, monthly, or daily, let n be the number of compoundings per year. So n is number per year. And t, again, is still years. So that takes us to something that looks like this. The amount at the end of our investment period is going to equal our principal. Again, 1 plus the rate divided by the number of times to the power number of times times the number of years. So, for example, if we were to compound interest monthly, that means 12 times per year. That's the number of times compounded monthly. And we were to do that for 3 years. That function would look like this. The amount of money at the end of that 3 years would be our initial invested principal, 1 plus, well, let's say we have a rate of 3.5%. We're going to put our rate and our number of compounded times as a fraction. That rate is a decimal, 3.5%, 0.035, over the number of times that we're going to compound, which is 12. And we need to raise that to the n, again, the number of times compounded times the number of years. So simplified, our formula would be principal 1 plus, if I simplify 35 thousandths, divided by 12, 0.0029, and we're going to raise that to the 36th power. Now, of course, we don't know an amount until we have determined the amount of principal that we would like to invest. In comparison to that, we, I'm going to erase that. We're going to back up here. This is a fascinating part of this. We looked at this formula, 1 plus 1 over m. M was the number of times per year, and in continuous compounding, that's approaching infinity. So we recognize this part of our formula, this part right here. I'm going to put a big red circle around it. 1 plus 1 over m to the m, and then to the nt. The part in red, if we think back, 1 plus 1 over x to the x represented an approximation to the value e. So our new formula for continuous compounding becomes P times E and that's to the R. Made a mistake up there, to the RT. So APERT, the amount we have after we've invested a certain initial principal, compounded continuously